Well, I mean, it does the catalysis, but the question is, what's doing the catalysis? Is it the functionalized dendrimer, or do you have cleavage of the metal carbon bond? So it's kind of difficult to assess that. But people are still using dendrimers today. I mean, there's still quite a lot of research going on in this area, but the 1990s, early 2000s was sort of the heyday of dendrimer work, to my opinion, and now it's sort of died down a bit. In chemistry, you always have sort of a favorite flavor of the month, and then it dies down after a while. All right. Now, what I want to do in this last hour is I want us to review the whole course briefly. And I want us to end off today's course by looking at some examples, which we've sort of been doing every, when we have some spare time, how we can design multi-step synthesis using catalysis for organic chemistry, which I think is very rewarding. If you have a target molecule and you can design a rational synthesis in as few steps as possible to make a useful starting material. But let's just have a look at the course again in total. What did we learn in this course? And what were things that sort of ran through it as connective themes? Well, obviously, one of the most important things is that we start off with a substrate and we end up with products. And the question is, the two issues always are selectivity and activity. In other words, how active is the catalyst and how selective is the catalyst? And remember, we distinguished 4 different types of selectivity. Can someone mention those? Stereo, yes, but we distinguish 2 types. Enantioselectivity, diastereoselectivity, regioselectivity, and chemoselectivity. Yes. I've never liked that word because it sort of, chemo reminds me of someone undergoing treatment for cancer, but yes. And we looked particularly in this course at homogeneous catalysts and always came to a catalyst cycle. And catalyst cycles, the thing I hope that I sort of really impressed upon you is there are essentially 3 things. What is the rate determining step? What are the resting states that we need to determine by looking at energy calculations typically? Looking at the intermediates in the proposed catalyst cycle, if they're reasonable or not, in terms of the d electron count, the valence electron count, the oxidation states, etc. And very important, the elementary steps. And we looked at all of those, and we encountered them again and again. And the thing is, the great thing about this is that, it's not about learning catalyst cycles. Once you understand the elementary reaction steps, you can actually predict what's going to happen. The other nice thing about it is, in terms of assessing the plausibility of intermediates, well, I mean, you can actually look at organometallic chemistry and see if there's a precedent for isolated compounds that may be intermediates or resting states along a catalyst pathway and use that to infer whether a certain reaction is reasonable or not. I mean, we just had the example in hydrocyanation of that 5-coordinate system, right? That's a reasonable intermediate. Or, for example, the olefin complex that we encountered, which resembles Zeiss's salt. So one needs to always look at these things depending on what catalyst cycle we've looked at. We looked at stereoselectivity. I think this was another sort of recurring theme. We saw that with a polymerization. We saw that last week with hydrogenation. We saw that today with hydrosilylation. And so these are the important things. So what I want us to actually do is now just go through all everything we've looked at and revisit everything, just so that we make sure we're all on the same page. We started off the course by looking briefly at heterogeneous catalysts and comparing homo and heterogeneous systems. And in particular, we looked at the Haber-Bosch process in quite some detail. And we looked at homogeneous models of the Haber-Bosch process, the work done by Schrock. And we also looked at Fischer-Tropsch catalysis as heterogeneous systems. We distinguished two main types of activation pathways or mechanisms for heterogeneous catalysis. The so-called radial or eddy radial mechanism and the Langmuir-Hinshelwood mechanism. The latter involving activation of both substrates at a metal surface, strong activation, chemisorption. Whereas in the eddy radial mechanism, only one is strongly absorbed, chemisorbed, and the other may not be absorbed at all, or it has a weak so-called physisorption. So we distinguished between physisorption and chemisorption as key steps in heterogeneous catalysts. We looked then, in the second part of week one, we looked at the elementary steps. We looked at all of them. Here are some of them: oxidative addition, migratory insertion, reductive elimination. But we looked also at sigma bond metathesis, which is something that occurs particularly in early transition metals and F-block elements, because they don't have access to high oxidation states. We looked, what else did we look at? What other elementary steps are there? Transmetallation, yes, yes, which is at play in CC coupling reactions, for example. What else? Yes, I represent this here as migratory insertion. I mean, strictly speaking, it's a type of a migratory insertion. Better would be to call this what? An alkene insertion into a metal hydride. Okay? Migratory insertion in the, let's say, conventional sense is, for example, if you have a CO inserting into a metal carbon bond to get an acyl complex, which we saw incidentally in which catalyst process? Well, in carbonylation reactions. That's one of the key steps. Remember the migratory insertion into a metal carbon bond. What else was there?
Sigma bond.
Yes, I just mentioned that. Beta hydride elimination, yes. Beta hydride elimination affording, essentially if you have an alkyl undergoing a beta hydride elimination, you get an alkene hydride. That is a key elimination step in which process?
Hydrogenation.
Yes, and also polymerization. Well, this is hydrogenation. Here we don't have beta hydride elimination, we have reductive elimination yet. But also in polymerization, remember you build this long chain via the Cossey-Ullmann mechanism or the Green-Rooney mechanism, which was discredited. And then you have the beta H elimination and you basically generate an alkene hydride. The alkene is displaced by a competitive alkene coordination, and then the cycle starts again. So understanding these elementary steps is the key to understanding catalysis, right? We looked at alkene polymerization. We looked at particularly group 4 metallocenes. We looked at the Ziegler-Nutter mechanism in detail. We looked at different activators, co-catalysts. We looked at using MEL, which is poorly understood, but seems to activate unreactive pre-catalysts. It is hydrolyzed aluminium alkyl, partially hydrolyzed, which forms cage-like structures, and because of their size, you end up in the cationic activated state, the anion cannot coordinate and block it. So we have a high turnover of catalysis. We also looked in this lecture at stereoselective polymerization, tacticity. And we saw how we can drive the selectivity towards a certain polymer bearing a certain tacticity by, for example, building bridges into the backbone of the cyclopentadienyl system if we're working with group 4 systems. This is just one trick one can employ. There are many other tricks as well, which then, of course, restricts the rotation of the rings. It's locked into a certain point group, CS symmetric, for example, and that will then dictate the stereochemistry in the product, and Nicole gave us a lecture on that as well. Don't forget that the active species is cationic in the case of group 4 systems. It's cationic, zirconium plus 4, and you've got a counteranion. People often forget that when they represent the Cauchy-Ullmann mechanism, as we saw in the midterm. Remember, you can also activate it with boranes. If you activate it with a borane, typically, you're going to, because the borane is quite small, it's going to lower the rate of the reaction because there's a chance that it can block that coordination site that is activated by the borane. We looked at metathesis. And so we looked at alkene and alkyne metathesis. And we looked at the Chanvaux cycle, correctly elucidated in the 1970s, explaining alkene metathesis. We looked at different types of alkene metathesis: cross metathesis, self metathesis, ring opening, ring closing, ring opening metathesis polymerization. The mechanisms are all the same essentially and boil down to this mechanism here involving a carbene, 2+2 cycloaddition, and the formation of the metathesized product over here. We looked at alkyne metathesis. We looked at this complex, this key complex of Schrock, this tungsten tris terbutoxy carbine, well, kilodyne at Schrock type, tungsten +6, which is a great catalyst, for example, in doing ring closing metathesis, as we see here, which is an important step in natural product synthesis and is a very useful step to have indeed. I've actually represented it twice here. No, these are two different natural products. We looked at different types of catalysts. In the case of alkene metathesis, we looked at Grubbs 1, Grubbs 2, Hoveda Grubbs 1, Hoveda Grubbs 2. We saw how you can improve dramatically the catalytic activity by playing around with the ligands at the ruthenium center. And we saw that, for example, in the Hoveda system, Hoveda 2, you have a carbene and you have a coordinating ether functionality which can swing away and facilitate the coordination of the incoming alkene. So we saw how one can readily design catalysts just by changing the ligands at the ruthenium center. Next, we looked at carbonylation reactions. We looked at the Monsanto acetic acid process and the Cativa process. The difference between the two being the one employs rhodium and the one employs iridium. BP is the one that uses the rhodium one. And we saw that the active species is an iridium +1 square planar complex, which is very similar to Voskhorst complex in a way. Got the same electron configuration ultimately. And we looked at this catalyst cycle in detail. The key step being the migratory insertion and the reductive elimination. And this interlocking cycle here, where the product afforded from the reductive elimination from the iridium is then converted to acetic acid, our desired product, through this cycle here, from the feedstock, which is methanol, which is converted to methyl iodide oxidative addition, and then basically the result of that is that this guy here, this acid, iodic acid, is then converted to acetic acid by reaction with water and regeneration of the hydrogen iodide, which is in fact a very elegant synthesis. So we looked also at what is the rate determining step in this reaction, and we saw that by changing from rhodium to iridium, in other words comparing the Monsanto to Cativa process, that we have a 150-fold increase in the rate determining step. So the disadvantage, of course, being that iridium is much more expensive, but because the rates are so much higher and the catalyst is so much faster, in fact it is commercially viable. Next, we looked at hydroformylation, which is the addition of basically a carbonyl functional group to a CC double bond. We looked at this in some detail. We started off by looking at Otto Rühlen, 1938 Urchemie, the catalyst that he employed. The active species being this CHE3004 complex generated, this doesn't exist in a bottle, it is generated from dicobalt octocarbonyl, remember, CO2CO8, upon reaction with hydrogen in the syngas mixture that we employ to make these complexes. And we looked at the catalyst cycle in detail. We also looked at changing from cobalt to rhodium, as you see here, in this catalyst cycle, or hydroformylation of styrene. And very important, what we looked at in this lecture was this work of Tolman. The Coleman-Tone angle. The Tolman-Cone angle, I always get that wrong, and this electronic parameter, which he used to rationalize or attempt to rationalize rates and selectivities into isoselectivities for a range of systems. Remember that discussion we had, looking at those different phosphines? How one defines a Tolman-Cone angle and how one actually defines the Tolman electronic parameter. So we have the electronic effect of the phosphine and the steric effect, and both of those play a role to some extent in rationalizing activities and selectivities. All right, and finally, we looked again in some detail at palladium-CC coupling reactions, all of which ultimately, essentially for better or worse, come down to this catalytic cycle involving a key oxidative step, oxidative addition step, a transmetallation step, and a reductive elimination step, except for head coupling, where we don't have the transmetallation step. Remember, we have alkene coordination and then coupling. This process is used for sp2-sp2 coupling, typically. The only difference between all these different variations, Suzuki, Negishi, Kumada, etc., is the choice of transmethylating reagent. That's all, in essence. We typically need to add a base. We looked at that in detail. And the active species is typically a palladium 0. In some cases, one can also use nickel. And you can do the reaction with palladium 2 precursors, for example, palladium acetate, which then generates in situ, under the catalytic conditions, the active species, which is palladium 0. We also looked at Sonogashira coupling, which is an example of an sp2-sp coupling, where we can, for example, couple arenes to alkynes. Remember? Very useful synthetic strategy. We then looked at hydrogenation. We looked at this again in detail. We started off with looking briefly at heterogeneous systems. We discussed Rayleigh-Nickel. We discussed also the Lindlar catalyst. Remember, very useful. Don't forget it in your toolbox. You can go from an alkyne to a cis-coordinated alkene selectively. That's a rare example of a heterogeneous catalyst that shows high stereoselectivity, incidentally. And then we discussed the classic complex of Wilkinson, this rhodium-1 compound, and we looked at the catalyst cycle, the first step and the rate-determining step being oxidative addition of hydrogen, followed by alkene coordination. We have insertion and reductive elimination to get the alkane, basically, or the saturation of the CT double bond. What we also looked at, which was, I think, quite gratifying, was what happens if you change the nature of the phosphines on the, let's say, first generation hydrogenation catalyst of Wilkinson, and found that you can tweak the activity of the catalyst by changing the electronic characteristics of the phosphine. The more electron pushing, the more electron rich the rhodium center, the faster the H2 activation. Why? No. Ligand association was a point, but if you take into consideration that hydrogen activation is rate determining, what is the reason that I get increased rates?
Oh, the sigma
Yes, yes, because remember, when hydrogen gets activated, oxidative addition takes place. It proceeds via an intermediate, which is a sigma dihydrogen complex, where you have a sigma donation from the sigma orbital in the hydrogen to an appropriate d metal, and a pi back donation to a sigma star orbital. The combination of those two weakening the hydrogen-hydrogen bond. And the more back donation you have into the sigma star orbital, i.e. the more electron-rich the metal, the weaker the hydrogen-hydrogen bond, and the faster you get to the classical dihydride. I realized after I gave that lecture that I missed out one important term, and I'd like to just mention that now. because I think it's a very nice opportunity to just mention that. We know, as we discussed, that you have, as an intermediate, a so-called eta-2 dihydrogen complex, which is a purported intermediate on the way to what we call a classical dihydride. Now, what a classical dihydride is, it is just a metal that has two hydrogen atoms with no hydrogen-hydrogen bond at all. In other words, what we've done is we've induced so much pi back bonding to these sigma star orbitals over here that the HH bond completely breaks and you get formally a +2 oxidation state here, right? In a sigma dihydrogen complex, this counts as a neutral ligand, right? And what's interesting about these complexes, of course, it's not like you have you have a dihydrogen complex or a classical dihydride, but there's a continuum, in fact, between the degree of activation of this H2 over here, right? And we talk about strongly activated and weakly activated sigma dihydrogen complexes. And you can study that by looking at the NMR spectra of these complexes, relaxation times, infrared spectra, and so on. And you can infer the strength of the hydrogen-hydrogen bond, which will tell you if it's closer to a classical dihydride or to a sigma dihydrogen complex. And if you get the balance just right between the synergic sigma donation and pi acceptor, you can actually isolate it, as Cubas did in 1983. Gregory Cubas. Very important result, because it proved that this reaction in this concerted dihydrogen activation proceeds via intermediates that look like this. We also looked at this business of the L-DOPA synthesis of noles in enormous detail. We looked at how one can change the stereoselectivity of a pro-chiral alkene in terms of hydrogenation by using chiral diphosphane ligands, the classic example being dipan, and you can make L-DOPA, because you as we looked at the beginning, you preferentially force only one of the two faces to coordinate. Don't forget that very instructive and useful quadrant argument that Knowles employed in trying to understand which face is going to approach the ligand. Another thing, or the metal center, another thing you can do, of course, is build a model to see that for yourself. You get coordination to this, forming a 16 valence electron intermediate. Then you get the hydrogen-dihydrogen activation, oxidative addition. The hydrogens are then mutually cis to each other. And then you saw, like we just looked at the beginning, you can actually see how the hydrogen inserts in a certain way to generate a chiral center, which we have in L-DOPA right here. That's the chiral center. All right. And today we looked at hydrosylation and hydrosilation. So just remember there, its importance in terms of the synthesis of adiponitrile used to make nylon. In fact, both precursors to nylon is generated from the adiponitrile, which is the basically six-membered alkane chain with CN groups at the end. And we looked at hydrosylation, ketone and alkene hydrosylation, looking at the Speyer catalyst, and then looking at Costin's catalyst, and basically ended off with ketone hydrosylation. I think we've covered a broad range of topics in this course. Also, don't forget what's important is the stuff we've done in the PBL sessions. And what I would like us to do now is I would like us together to look at some challenging problems employing everything we have learned. And this is something that you can expect in the exam. Putting it all together. So let's suppose I want to make this molecule. I want to synthesize it, And I want to synthesize it from the following precursor. So this is quite an easy one to get us going. This is the precursor we have available. And you can use any other precursor of your choice. Design a synthesis employing, in every synthetic step you must use some a catalytic procedure. Now what's useful in problems like this, of course, is retrosynthetic analysis, which you've done. Now, yes, they're cyclohexane rings.
From benzene.
Yes. Yes. Now, let's look at that molecule. That's quite a big molecule. I mean, I'm surprised nobody found this amusing. I mean, it looks like an animal, right? Did nobody see that? All right, now what's useful here is to break this down into building blocks. Retrosynthetic analysis, the Burgert way. I'm not an organic chemist, right? So I'm going to do it like an inorganic chemist would do it. So what we can basically do is we can break it down in the following way. Obviously we're going to, because that's the starting material, so that's a hint that we're going to have a disconnection here, 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 and here. That's obvious. And if we think about A, we can synthesize A and then basically get it onto this ring system here. And we can do the same with all of these others. So let's call that A, B, and C. That's one way of doing it, right? Break it down into simple building blocks, synthesize those, and then at the end you can sort of link up all the components that you've synthesized. That's how people do natural product synthesis. They don't synthesize it in a linear way. They synthesize building blocks that they then, in the last few synthetic steps, they sort of put them together. So let's talk about it. Let's talk about A. Now we want to make A, let's synthesize A. I've said you can use any starting material, but let's start from the simplest available materials we can think of. No, let's start with, let's in fact start for A with 135 tribromobenzene. So for A, 135, now you'll see why in a moment. We can't really start with cyclohexane, because if we start with cyclohexane, we're not going to be able to couple anything to it. Remember? We need the arene to do what? CC coupling. Can't do CC coupling with cyclohexane. So what are we going to do?
I have a question. Do we consider selectivity or not?
Very good question. No. I mean, selectivity is going to certainly be an issue. That's for sure. But you're certainly going to end up with a design product. You might have to do a purification by column chromatography or something. But you can probably minimize problems in stereoselectivity. Let's see if we can address that, talking about reaction conditions, right? So how are we going to do this reaction? What are we going to do to get A? We have a number of possibilities. Which one? For example.
That's the red.
I would use HEC. Okay. So if we take this and carefully control. HEC might be difficult because how are you gonna? You need to just get exactly two equivalents of ethylene gas in there. So that might be difficult. But I'm just thinking, maybe what would be better, in fact, instead of using HEC, because you see, if we use HEC, the problem is what? We have to use ethylene gas, right? And if we use ethylene gas, how are we gonna, that's gonna be a problem. Because, I mean, Heck does the reaction, you know, you can't just measure out 2 molar equivalents of ethyl. So what are we going to do? Another coupling reaction. Well, what about this? And one of the coupling reactions we looked at using a Grignard reagent. This is the transmethylating reagent. So, if we do that reaction, what are we going to get as a product? If we control the stoichiometry and we're lucky with selectivity, if you put in 2 of those, because of the symmetry of the molecule, you might be lucky, there might be selectivity issues indeed, but you may get that one enough that you can maybe purify it from the other side product, which may be the tri-substituted one. But chances are you're going to get high selectivity towards that because of the symmetry of the thing. So what can we do now?
Add Suzuki coupling with another benzene.
We could do that, but I would get this building block.
Hydrogenation.
Yes.
Another question, is there a bit superfraction, do you need a double bond on the
We don't need. We do
Yeah.
need the double bond. Remember, because it's sp2 coupling.
But wouldn't it work just by Grignard? I mean, just a normal Grignard addition without having that?
The Grignard reaction of an aryl halide with a vinyl halide would work, but it's very slow. Very slow. So you'd have to stir it for a couple of days, whereas this reaction, you'd have the product in a couple of hours. Remember, we discussed that in the beginning of the CC coupling. You can do CC coupling with Grignards, but it's cumbersome. This is more elegant. Remember, this is also about elegance and synthesis. Yes.
How can we like hydrogenate OT5 removing the Br group? Like, wouldn't that also
No,
be
because the
nice
carbon
as
bromine bond is pretty strong.
well? Okay.
So we need to hydrogenate it, but we need to be careful because we don't want to use a hydrogenation catalyst that's too powerful, because then we're going to hydrogenate the A-ring ring, and we can't do that because we need to couple it in the next step to this core here.
Can't we
So-
do all the coupling and the hydrogenation in the end for everything?
All right, shall we do that?
Okay.
I think one must be careful, because if we do that, in the next step we might get a competitive Heck coupling, because we've got alkenes there. And if we react that guy with this guy, we might get a Heck coupling. You see the problem?
Yeah.
Got to think about these things. So I suggest we hydrogenate carefully to get, but we don't hydrogenate the A-ring ring. And what are we going to do for that? No? Well, then I think you're playing with fire because it might be just a little bit too.
Strong.
Oh, no, actually, Lindlar might work, but that's.
It's not gonna hydrogenate the benzene.
No, it won't, but Lindlar's more suitable for alkyne hydrogenation. So let's use another one. Wilkinson. Wilkinson will work. It's mild enough.
So what is considered a harsh one?
Rainy nickel. So if we use Wilkinson hydrogenation, Connor, don't look so sad. He also has a sad expression on his face. We're going to get that guy there, the bird. So now we've synthesized we're now in good shape, right? Because now what can we do?
Suzuki.
All right, well, let's just now, we have this in a bottle, let's put it to one side. So this is building block A. Now, building block B is, okay, well, I mean, what we can actually do is we can now actually proceed with a coupling directly, in a way. So if I were to take this and react it with this and do a coupling reaction, I would get the product. Which coupling are we going to employ?
Suzuki.
So we're going to use boronic acids. All right, why not? How are we going to make it? Yes. We're going to react this with magnesium bromide. We're we're going to get this guy here. And then we're going to react that with boronic acid. Well, basically BOMe3. You start with a trimethoxyborane, and we're going to get this guy. With, of course, magnesium, BROMe. And then we're going to do a deprotection, and we're going to get the boronic acid. Now we're going to do the reaction with this and this. Which catalyst shall we use? Palladium 0. Let's use palladium PPH3-4. We're going to use this here. Let's just write a plus here, these two. And don't forget we need a base. What base are we going to use?
Sodium carbonate.
Sodium methoxide is good. You can also use CH3 cook. All right. And
Can you use sodium hydroxide?
sure. Sodium hydroxide works as well. Very important to add the base. Remember why? Because it not only replaces the halide on the palladium center, but it also activates the boronic acid. Now,
Sorry, another question. Why do we need to go to BOH and we can keep BOMe?
in other words, why don't we just start with BOH?
No, but I mean, like, you transform BOMe into BOH. Couldn't you just use BOMe?
No, you use BOH.
And then why do we do BO? Like, why do we put a methyl group on it? Couldn't we
Because
just make it
because BOH3 is unstable. The reaction doesn't work. In other words, what you're saying is, why can't we react this with BOH3 directly? Doesn't work. You have to, that's quite a sensitive reagent. Remember, it's Lewis acidic and all that. So you have to do it via this sequence.
So we make that one in situ then, the BOH.
Yeah, you can make it in situ, but it would be advisable to isolate it. Right, because then you're going to end up, if you don't isolate it, you're going to end up with unreacted Grignard reagents and all sorts of things, and you're going to end up with soup. So it's advisable to isolate, try and isolate and purify that guy, if you can. Now, we're going to do this reaction. Now, of course, we're going to have problems here with selectivity, aren't we?
Actually, no. Oh, yeah.
Are we? Well, potentially. Potentially, we're going to have problems with selectivity.
Can't we start again with the dry substituted instead of the full?
No, because remember we need to attach other substituents here later on. So let us do the coupling and assume, okay, we're going to have selectivity issues here for sure. But we can overcome those probably by separation, chromatographic separation. Okay? So, which is a reality in chemistry. So we're going to now couple these two guys. All right. And we're going to have a bromine here, a bromine here, and a bromine here. Plus other products, which we can separate out by chromatographic separation. What's the next step? Now it's easy. What? All right, we can do that. We can do that. What we can also do, however, which would be more convenient, is just to take this. I mean, there's lots of possibilities, right? We can take, for example, this and do a head coupling. Can't we? If we do a head coupling, we should get, again, there's going to be selectivity issues, but one of the products certainly will be this. Does everyone agree? Of course, I could have employed another Suzuki coupling if I wanted to, but I can also employ HEC. In other words, I'd use palladium 0, palladium acetate. Let's use some other reagents in the presence of CH3 Cook. And you'd get that product. Selectivity might be a concern. We might get some mixture of tri and di substituted, but we will probably be able to separate by chromatographic separation. And what's the final step to get? Well, not the final. What's the next step?
Let's get rid of that double bond.
No, okay. I suggest before we get rid of the double bond, what do we do? Whoops.
Oh, do the last.
We still have double bonds here, don't we?
Yeah. Yeah.
Oh no, I didn't.
No, we hydrogenated them.
We did hydrogen. We did more hydrogenation, but I've got double bonds here, right?
Yeah.
All right. So what's the final step? I need to build in this funny-looking thing at the bottom here, the feet of the molecule. What am I going to do?
Very good. Just
Oh, you need to add the last part, right?
Yes.
so you can
It's more hectic.
Can we?
can't use like any of the others in the
Remember, there's a carbon here. You want to use Sonogashira. The Gishi.
Yeah.
Okay, so tell us what would you want to do?
I don't know.
She just wants to use the Gishi.
Isn't that with the thin? No, that's Stille.
That's Stiller coupling.
You can, in principle, use any of those couplings, right?
In principle, yes.
Magnesia.
I would employ, what would I employ? I would employ well, with Stiller coupling we have sp2, sp3 coupling, don't we? Let's just go back to, it's sp2, sp3. Let's go back, let's just review Stiller again, just a second. Because I think Stiller might be the answer. Oh no, that's catalytic hydrogenation. My sincere apologies.
Lecture 7.
The lecture 7.
I'm just a little confused with the cycles because we put in our chain, we never know exactly what the structure of the R chain should be for it to work.
Well,
To me, like they all look the same, but they don't all work.
well, it's sp2, sp2 every time. So it can be an aryl, it can be a vinyl, it can be, as long as it's an sp2 hybridized carbon. It's not that complicated. All right, so there we have Stiller coupling. It is, I just wanted to check that. It is sp2, sp2. So what can we do? What can we do to get this foot of the molecule man in there?
Well, would this count as like a terminal element?
Exactly.
So then we could use an alkyne.
An alkyne, so a Sonogashira coupling. Would that work? No. We've got to be an RB especially creative.
Thin
It's annoying that
dye
there's not enough
alkene
more.
complex.
Because, you see, we're not actually, this is an sp3 sensor, it's not an sp2 sensor. So all our coupling tricks are for sp2, sp2, right? Except for Sonogashira, which is sp2, sp. So that's a difficult one. I think, I'm just thinking, I think it's going to be difficult to do with coupling chemistry. So I think what, to get this guy on, I mean, I actually can't think of a coupling reaction that's going to do that. Do you see the problem? Because it's sp, we're trying to do sp2, sp3 coupling.
Can you put in the for measuring the
Yeah. Oh yeah. Then ring opening. or
Yeah,
something
yeah,
like that.
that's good.
That's very creative. Very good. Well, let's think about that. I think that's a stroke of genius. So what you're saying we should do is we should take. Let's think about this. If we take something like this, and we do ring opening metathesis.
You need
5
5
members.
carbons. Yeah, you need 5 carbons.
5 members.
1, 2. Yeah.
Is it
Yeah.
5?
Okay. But you see, the problem is the attachment point is still the sp3 center. Unless, wait, yes, we can do something like that. We can attach, yes, that's how we're going to do it. We're going to do head coupling with that, right? We're going to do head coupling with this guy, the cyclopentadiene. And we're going to get this as one of the products. Selectivity might be a concern, but let's ignore that for the moment. So we're gonna have, sorry, I hope you can all see this. We're gonna have that. Does everyone agree?
Mm.
If we do head coupling between the alkene and the bromide,
Yeah.
using palladium acetate, so the same thing, palladium acetate base. And in fact the selectivity will be quite, well, we might have coupling in that position there, but okay. So what now the stroke of genius is, what do we do now? We do ring opening metathesis. And if we do ring opening metathesis,